In this post, we look at a search engine implementation on top of the data that is already available within the application. The application holds a list of web pages, and for each of the web pages, a set of word counts have been generated. This is done at regular intervals, and the purpose of generating the word counts is to show word clouds. The same data on the word count can also be used to build a search index, which is a compressed trie data structure, and it can be used to implement a search engine. So we have a basic search engine that has been implemented for the application, and let's search for, let's say, Python programming, and it will look into the trie index and bring up the list of web pages within which these words occur. Let's look at a name. So here we see the list of web pages which have the name of the US president mentioned in them, and we can also see that the search results are paginated. Let's look for, let's say, Apple Tech News. So this is the list of pages which mention these words, and we can see that there is the CNET Australia Tech News website and also the CNBC World website. And for each of the search results, we have a title, the actual URL that was crawled, and the URL at which the words occur, and the timestamp at which this particular word was encountered on the web page. So let's look at how this is implemented. This is implemented by first crawling the web pages. This has already been part of the application, and this is the architecture. The crawling is actually done on Celery async tasks, and the word count generation is also done on Celery async tasks. And the data structure that is used to hold the search index is a trie data structure, which is an emery tree where each node branches out to child nodes based on one particular character within the key. So if the search string is Python, for the letter P there would be a branch to a particular node, and from there for Y, and so on until we reach the set of web pages where the word Python occurs. So this is implemented as a search tree and also a compressed search trie, and it will be part of the PyCoils data structure library, and it is compressed from, let's say, 21 MB on an uncompressed tree to around 7.1 megabytes on a compressed tree structure. So for the compressed tree, we are using an M by N sparse matrix, which is if there are M nodes within the search tree and N characters within the character set, that is for all the web pages within the application. When the web pages are encountered and processed, as a character set is built, and if N is the total number of unique characters in that set, then our sparse matrix is M by N, and of course it uses scikit-learn's sparse matrix, and the index is generated, the index is searched for each of the words, and a set of web pages is retrieved, and a set intersection is performed, and the resulting data and with selected information or data points is sent back to the user as search results. So that's how this particular search engine is implemented, and it has got reasonable response times, and the size of the search index for, let's say, in this particular example, 79 web pages crawled, let's say, twice every day, and the index is generated daily. The size of the index is 7.1, which can be effectively held in memory, let's say in cache. So that's the web page search index that has been built in this particular iteration.